I work on massive stars. I know very little about common envelope, so I think most of us don't know much about common envelope for massive stars. I think for the massive star, it's quite an unexplored territory. Let me do. I'm just filling the time so people that still are getting coffee can. I know most of you by now. For those that don't, I'm still in Amsterdam with a few fantastic people there. I'm moving to this coast to CFA over the summer. It's a pending visa, so I don't announce that too widely. Stephen Justin will likely stay in Amsterdam for a while, and we try to run a transatlantic group. However, that may work. That's still depending on all kind of funding uncertainties that we're still figuring out. I'm mentioning Stephen Justin here because he's also very interested in stellar mergers, saying failed common envelope events and such. So yeah, should have probably had him here, but too many meetings. So most of the discussions we had were, and the simulations we saw were for low mass stars, right? Traditionally, we thought of common envelope evolution as pathways to produce these main products of compact white dwarf binaries or double white dwarf binaries, and that's where most effort has been going. And I'm starting to learn from several people and discussion with Ursula. It's so hard to do these massive stars, so it's I think relatively unexplored. But it is the area where I think the new data is streaming in as we speak, right? My phone may go off and there will be another LIGO trigger, and I'll be excited to see what the next one is coming out. So especially the gravitational waves is going to deliver that at a rate, but it's at the very end of these binaries. And there may be multiple pathways to get there. So it's not so clear that one answer will roll out. It's not so clear that after 100 detections we know this is alpha common envelope, right? Apart from the simplification of the physics of the common envelope process itself, there's multiple pieces of physics involved to get there. But there's more areas where data has been improving and is improving that is maybe less in the spotlight, maybe not Nobel Prize worthy, but still very constraining for the course we're thinking. Largely unexplored computationally. Paul is saying he's doing a massive star common envelope, but how many? I didn't have an overview how many simulations we have today. Is that one of the few?
A couple. Oh, you mean just in general across the field?
Yeah, yeah.
3D ones. I think the previous ones that went above 10 solar masses, let's say, would have been rectangles.
But I think we should also count efforts like Fabian Schneider is trying to do, and other people. Common envelope is not just about ejecting the envelope. A large part of the physics will be which ones merge and come back there. And I think this is sort of the gist of the first part of this discussion. It's not just a scaled-up version of low mass. There's many, many differences. We may ingest a neutron star or a compact object. The stars have different structures. I think there's much larger diversity in the progenitor structure and their composition and their density structure. That makes a difference. So this could be the summary of this talk or the large part of the conference. Yeah. I don't know what's most useful here. What I decided is I'll talk a little bit about, given that we have so few observers, I'll try to talk a little bit about observations of the progenitors and immediate products. And the second half I'll talk a little bit about gravitational wave population synthesis. And not because we know what we're doing, but we need to start from somewhere. It will be an iterative process. So there is some structure in this. The progenitors. So what do we know about massive stars? Balls of gas held together by gravity, and their evolution will be quite different depending on the composition of the gas that they're made out of, and that's particularly important if we think about gravitational waves, because these heavy ones, maybe they were not made from the composition that we have in our own galaxy. We don't have much opportunities to study what stars do at low metallicity, but we have the Magellanic Clouds, which are 1/2 and 0.2 solar. In the simulations that people are running today, we think that these 30 solar mass black holes primarily come from things that like a 10 solar or less, right? We'll fight over what the number is, but so we don't really see the immediate progenitors of those heavy things, but we might be seeing the immediate progenitors of double driven stars. So what do people do? So this is work for collaboration that of it, I think 40, 50 observers mostly, and then people like Matteo and Mia hanging around. This is the 30 Dorades. Sorry, let me go here. 30 Dorades is this little smudge here, and it's one of the most actively starbursty regions that we have nearby. Extragalactic people will laugh at us for calling it a starburst, but so we have about 1,000 massive stars that people can take spectra of and really study in detail. And sometimes this gets the press attention, in particular work of Paul Crowther, because in the very center we might have stars of 200-300 solar masses. Just a handful. It's not that we know how they live their lives, but we see them in their long-lived phase. And so this has been sort of the challenge. This is the classical diagram that any evolutionary theorist would make over and over, showing the evolutionary tracks of these stars. So in light blue you see tracks for 10 solar mass to 200 solar masses, and in the dashed you see the isochrons for this particular model set. These are models a bit similar to the MESA codes, but this is the Bond code. And so this part of the diagram has been mostly really scarcely populated for a long time. And this particular survey put these data points on. So maybe that's the point where you start to wonder, do these models do a good job? This is not the only data we know for these systems, right? We have some information for some of them about whether they rotate, whether they have a companion, a bit about the surface composition, although these particular spectra are not the highest resolution. We may know about the stellar winds at these stages, but the big problem is two things. They're still rare. I mean, it's relatively empty up there. And yeah, massive stars are short-lived. So the only phase that we catch is their main sequence evolution. If you want to understand the progenitors of common envelopes for massive stars, they can do that late in their evolution in a very fast phase. So it's not that it might be hard to see the really immediate progenitors. And so one of the big questions, and if I'm organized enough, I'll come back to that at the end of my talk, is how big do stars get? Which is the important question. Do we even understand that? Maybe that's more of a, yes?
So if you try to understand, I think the number density of points across that HR diagram, how well can you do it?
Well, it always comes back to, it's a bit obsessive, but what is the predictive power of the models in the first place? So even if we keep all the physics the same, that we mixing winds, etc., then even minor differences in treating the outer bit of the envelope can make enormous differences in these tracks. And Matteo is the person in this room to talk about that. And so, do we even have predictive power to say where these lines go? And I'm not even talking about the big uncertainties like mixing. It's just how to treat the outer bits of the star.
So maybe it's something to add. Are all these tracks evolved till the end of hydrogen burning, or
yeah,
even the one at 200?
I'm co-author, but I forgot now. I think they're all completed till the end of.
So one of the issues for those more massive stars is that they're radiation dominated. We do not understand energy transporting the other layers very well, which couples to muscles, which is the other big uncertainties that kicks in for those stars. And so there, the solution picture is incomplete. So the predictive power, I would say, is low.
So try to go back and forth. I would say for most of the evolution that matters, namely the expansion phases, I think we have many open questions here, but it's not so bad at 20 solar masses.
Right.
But there we are not in the dark. But
it's really interesting in LIGO for organic Earth. That's where we want to.
Well, I mean, so this is, well, we don't know this actually. We don't know. I guess this is the neutron star progenitors.
Sure can.
And that possibly the black hole progenitors, but even that is a debate. But at the moment, the black hole binaries come in at a higher rate because they're so loud. But it looks like we have two. In case you didn't follow, it looks like the second neutron star merger happened. A bit far. I don't think there was maybe the secret detections of an EM counterpart, but I haven't heard of it.
This is one of the 26th you're thinking of?
There was one maybe 1 week.
There was
ago.
April 25th, April 26th.
Yeah. Oh, yeah. I didn't remember. Yeah, that's 1 week ago.
The second one was like 400 megaparsecs.
Yeah, and if any of you is not in the loop, there's also a tentative detection of something that could be a black hole neutron star. The false alarm rate is not great, but I mean, these things are going to come in. I think that's the.
But an important point is what you just said about neutron star. You're right that those would come from this object, but they are merging, so they probably went through common envelope phase. We learned that common envelope maybe drives up the luminosity to mass ratio and create objects that maybe are more similar to the star at 860 or 100. So you put together
Later,
the star.
after.
Later.
Yeah.
Right, but
Well, most of these are happily waiting to do anything
Sure,
fancy, right?
sure.
So most
If
of
you make
the
a
models
single
for the formation.
star, there's no problem.
Yeah.
But two together close by, well.
So in this data, how many of those points have independent determination of the mass of the star, say because they're in a binary system, so that you can really.
Very few. There's a couple of for the O-type stars. O-type stars. It's roughly what would it be? This bit. There is 300 stars in the. This is not all the stars in the sample actually. This is a subset of well-determined parameters. There's 300 O-type stars. 100 of them are single-line binaries. That's not enough for a mass. I think maybe 20 are double-line binaries. There's a very small subset that really has an independent mass.
So these are the selected single stars, right? This sample.
Also, yeah.
I mean,
Well,
non-detected binaries.
there's no. These are the ones that had the most beautiful spectra. They weren't too messy. There was not a source next to it, and it wasn't moving much. So if there was a companion, we don't think it was messing up. This particular diagram was made by Fabian Schneider. You also know for this merger, but here he was playing an observer basically. This was to try to determine the initial mass function in this region. So, but it's the most beautiful one.
But is there any hope to sort of calibrate the models that you're talking about, where you really have the mass and the position of the HR diagram?
Yes, but most of these systems are with two main sequence stars, right? And so the real questions we have, how do things behave when they swell up?
So you only have main sequences.
Well, this survey was selected for hot stars. I mean, there must be. Well, so one of the questions, I guess, and I'm not the best person to talk about it, we should get to Ben Davies or people in this population of red giants and red supergiants. That's a very important part of the diagram, right? Do stars swell up all the way here, such they can actually be convective and fill their envelopes? If this is empty, that doesn't mean they swell there. It could also mean they swell, but they stay there for a very brief time, right? So that's. If you take Belchinski's or someone's model for the first event, as Paul also did, you would get, what is it, an 80 Solomon star, but it is assumed that it swells all the way to become a red super.
Yeah, that's right.
Great.
Yeah, I'm fine with this. We have an hour for massive stars and massive star discussion, and my talk is reasonably unorganized that we can take any discussions on the way. These things are common. Whatever we do here, whether the envelope is ejected successfully or not, or whether it's actually ejected through stable mass transfer, this happens a lot. This is a beautiful paper from Max Moe, and it's an overview and a compilation of all the studies on how many binaries do we have over different mass ranges. And so this particular plot says how many companions do you have? It's not yet the question we should be asking, but let's start there. And so solar type stars, is half of them don't have a companion. And these O-type stars, they have more conventional relationships with multiple stars there, at least two. That's not the right question because they could be far away, right? Oh, I'm going the wrong order. This came up a few times, but there's data for this, right? What is the multiplicity fraction? And so solar type stars, they are mostly alone. This is the binary fraction, like 30%. Actually going down for massive stars, the binary fraction. Why? Because the triple fraction goes up, right? And so this is the triple and the quadruple fraction. So let's say 20 solar mass star, we have 30% in triples and quadruples. We have to double check how the counting is done. That's also not the question because we don't know how far away these are and if they really interact. This is, I think, the most useful plot for us if we want to think about binaries for the moment. And so you cannot read this, but this is the fraction of stars that have a companion within a period range for interaction, so close enough to interact, and a mass ratio such that it will probably do something severe to the star, right? Point more than 0.1. So that's a subset, and that's what's shown here. So what does it say? A solar type star, a certain fraction interacts, but I don't know, you can get away with single star models for population maybe, not for real events. with these definitions, 10 is Sholomar star. So these are the dominating progenitors for Newton stars. Most likely, 60% will interact, and there it's basically 100%, right?
So focusing on the low mass end has been looking at the smallest fraction of the cases that actually interact.
Or you have to take the IMF.
Most stars, most the IMF is in your favor, but
That's
yes. So there is something funny. Well, we can come back to that. But if we look at gravitational wave events, so I find this a funny contrast, right? This is very, very common. Every massive star is in a binary. Yet gravitational wave events is 0.1% of the final outcomes, right? And so it's a bit dangerous to take such a rare outcome to learn about a process that's so common. And apparently only very few cases make such a rare outcome. That's something to keep in mind. So let's get excited about gravitational waves and put it in our funding proposals when we want money for this. But maybe we should also look at the boring outcomes of common envelope evolution. Maybe these stars just merge and look like a pretty normal star. But let's look for magnetic fields, or I don't know. Maybe we don't have to do this in detail. So for the massive stars, that's the part where we contributed with Huxana primarily. And so it's not just how many are in closed binaries, but also how are these separations distributed. And so for a long time, the easiest thing you can do is draw a straight line, and that's Öpik's law. We have a beautiful name for it. It's 1924, I think, is this paper. And what does it say? It's a cumulative distribution, and it says there's as many binaries between 1 and 10 days, 10 and 100 days. And so it's flat in log A is a different, flat in separation or flat in period is the same. So massive stars, what do they look like? This is our science paper from quite long ago already. And so this is Huxana's distribution. You see all these closed binaries, right? Each of these is an individual binary system, and there's all these systems with periods less than 10 days. So if you think about common envelope evolution, we're not just talking about red giants filling their envelope, but if you have a bit of more open mind, we should also think about common envelope of two main sequence stars that touch and make some sort of contact system. Maybe we need a different meaning for those, because, but still, do we call that a common envelope system? So there's many of those. Of course, there's selection effects, but the selection effects here, you're very complete for these short period systems. It's very easy to catch eclipses or radial velocity variations. Out here, you're less complete. So this was 2012. I just wanted to show you that what happened. Happened afterwards very fast. Is it working? Ah, good. I spent so much time making research. So there's at least 3 or 4 different surveys. And so this is showing the distribution. So this is, in yellow, it was regions in our galaxy, young OB type regions. The orange ones is also our galaxy, but it's O and B type stars, so it has lower mass, but a different study, independent people. The red one is 30 Doradus, so now we go to the LMC. And then this one is not published, but this is the most amazing sample. This is basically all O type stars in our galaxy. And Huck forcefully extracted this to start showing it in conference proceedings, but their actual paper is not yet out, but it's a fantastic survey. And so all these have high binary fractions and show similar distributions. Anyway, so yes, they're common, and so I liked, so Morgan, I liked, you showed me a paragraph where you made the case how common these things are, and that even 10% of massive stars do it. No, it's a way larger fraction actually. So it's the majority of stars will go through something like this. How am I doing? I should keep some track of time. So let's go to. Oh yeah. Yeah. Before we go to the gravitational waves, I want to talk about a bit more immediate products of common envelope. We could talk about many things, but I'm interested in these. And so let's say we have a binary system that one star fills its Roche slope and say it decides I'm going to come unstable, strip off the envelope, and what do we leave? We leave one core and just one regular star next to it. And so we know of these systems. Such stars, if this helium star is massive enough, it will have a wind and emission lines, and then these things are called Wolf-Rayet stars by observers. Theorists and observers use slightly different terms, but these are known, and this is pretty old catalog. There must be newer data. I think we should explore these products again, how complete these data are. But in this particular survey, there's 20 Wolf-Rayet plus O-type binaries, and there's a couple of examples. And all these Wolf-Rayet stars are massive. There are 10 solar mass and above for these helium stars. And so here's 3 that are in 2 days, 2 days, 4 days. There's no way you can make this with stable mass transfer. Well, I don't know. Well, stable mass transfer is going straight out L2 or something. I don't know how to do that. These 3, at least Jelena Petrovic tried to see what can you do with stable mass transfer for this. But this must be common envelope products of the most massive stars, right? A bit of a paradox for a while was all these Wolf-Rayet stars, they're 10 solar mass and over. But this is it's the core of a star, right? The typical core of a massive star would be 3-ish solar mass of helium, 4-ish. That's enough to make a neutron star later. So where are all those? But that's something I'll plug a little bit. Let you speak first, Enrico.
Do we have an idea of how long the nebular phase in this sort of mass ejection will last, and whether there's any hope to see the?
People quote like 10,000 years, but
I think much longer.
much longer?
No.
I mean, if you're rejecting 5 solar masses, 10 solar masses, you have huge ionizing radiation.
Yeah, but after 10,000 years, we don't see much.
I do talk a lot to Philip, so this is not an independent statement of the time.
It's a expansion velocity matters.
Yeah.
And these things happen in, I mean, we're usually talking about young things, and it's probably in the first few million years. There's other massive stars around, so it can be very messy areas within gas where stars are still forming. So it's maybe not so easy to see it.
You would mistake it for the star-forming cloud, maybe, or remnants of it.
Fuzzy.
That feels more convincing because, I mean, 10,000 years is a pretty decent fraction of the lifetime of these. So you don't have to look at that many massive stars to see, you know.
10 million years versus 10,000, there's still.
Yeah, so, I mean, there's a lot of stars though, right?
It's not many massive stars. Our biggest sample are within a mass range 100 to 1,000 stars, so we don't have that many. Yeah. Okay.
So how many of these are in clusters?
That I don't know. We can look this up. I think my main point here is I think we should revisit what's here. This is 2001. With some of our observer friends to make this more complete, or at least understand what the biases are in this sample, right? So that's. I think Huxana has a student is trying to get it more complete. So one of the bit of a paradox is where are all these helium stars that are less than 10 solar masses? Because I think 2.5 or so is probably still enough to make a neutron star later. Close to 3 would be possible. And so this is something we worked on, and so I'll briefly do a small advertisement for Ilva's work. And she graduated and did her thesis in Amsterdam and moved to Carnegie observatories, and so she made models for such helium stars and tried to see what they look like, what kind of spectra would they have. So here's a whole sequence of lower mass helium stars going to higher and higher mass. And so these highest mass stars, I know there's only one observer here, so I can say anything I want. But these high mass stars, you see these emission lines, which people would start to call Wolf-Rayet stars. The low mass end here might be a bit more careful maybe. This is what this is particular absorption rates that people would probably classify as subdwarf B and subdwarf O stars. And so in this intermediate regime, that's the stars we have been missing, and you have this hybrid spectra of having absorption and emission at the end. It's one continuous sequence here. That's the theorist view. What has been excited that have been claims for a new type of Wolf-Rayet star. Oh, there's emission and absorption line. What could it be? But this was what Ilva had in her on her desktop computer, right? So we really get those stars in this intermediate masses. But we see very few. Well, why? Well, there's something. This is wavelength, of course, and this is interesting part. If you like ionizing photons, it's not a great part to look at. And so above here, you can see where we can actually look. Like this is even if you take UV and look from space, the IUV and Galax and the more bluest part of HST, and this is part of the spectrum you see. Whether they peak in this place where we're all blind, right? The only emission that was there was the EUVE telescope, which didn't see much. Why? Well, it's not just that we are blind, it's also any bits of hydrogen in our interstellar medium is actually blocking. So there was almost no source of it. And So that's not what we see, and that part is, well, good luck convincing an HST tech to find stars you haven't seen yet. And so you're stuck with this, say, the tail of the elephant and trying to find the elephant. But you can only look at the tail, and then on top of that, well, you know, there was a star that helped it get rid of its envelope. And if that's shining in optical, it doesn't have to be a big super star to outshine it there, right? And so here we have a companion star that is not that massive and bright, but it's easy to block this. That doesn't mean they're not there. If you know all this, you can say which ones are we missing and where should we be looking. I cannot show the data yet, but Ilva and Maria Drought, and as we have been looking at surveys, we have several dozen candidates. Maybe not all will have beautiful parameters, but we will start to fill in this gap of immediate progenitors. Very excited about it. Then, yeah, I don't think, I'm not going to say too much on the gravitational waves but this is one of the big questions. How do we go from two stars to something that people tattoo on their arms? Already not anymore. This was 3 years ago. This is where we are now, right? And so in main images here, I've put gray circles over the new black holes that formed, but this is the black holes we should be looking at and try to understand the outcome of massive star evolution and common envelope. Now for black holes, there's multiple channels that contribute, but I think for the moment, for double Newton stars, I think the only viable channel producing high rates goes through common envelope. And for the black holes, we have I think we can be a bit more competitive. The rates are crazy, and so one thing you could compare this with, I don't know what the core collapse rate is. These units, they don't tell me much. So Enrico triggered me to do this, and you can think about the core collapse rate, and it could be 10 to the 4, 10 to the 5, depending on who you want to believe in these same units. So what does it mean? You cannot do this, right? This is a death of a star immediately, and those black holes formed way earlier and took a long time. So we're not comparing apples from the same population to apples from the same. I don't know what it is. Either way, just to put these rates in context, what does it mean? That's like 0.1% of the local supernova rate. This is the one that can make people a bit uncomfortable. The Newton star rate is like 1%. Could be of the order of 1% of the core collapse rate. We have only one, that's based on the first event only, right? So we'll see where this rate is going with time, but 1% of the core collapse rate, that's interesting. Many things need to go right. The common envelope needs to eject. The stars need to make Newton stars not flee away from each other, but stay bound. So the models, I mean, they can do that. There's enough freedom in the models to get there. But if it's really the high end of this rate, that's going to be constraining also for common envelope physics in case. Right? And then there will be a large part of the physical parameter space that's out. But let's see. That was based on one event.
The second event shrinks this error.
Already? Yeah.
And maybe
Yeah.
it's 1%.
Are we on the, yeah, so I don't know the new rate estimate yet, but you have that.
Yeah.
Yeah, sure.
Also 3% of the point.
Well, it's from before April 24th. Yeah. Either way, these rates are on the high side, and so it's, yeah.
Someone for the black hole rate,
Just before.
I normalize
Oh,
that
wait, so
not
the
the
second
core
one's
collapse
not the
supernova rate, but the rate of core collapse supernova of stars about 20 solar masses or so.
Yeah. But
What
that's the one.
what would be the relative to that core collapse rate?
Does somebody wants to do an IMAP? What is the subset here? I won't do that here.
Okay.
And I think the more important thing is to remember, this is stars that died here today. Those are stars that probably died at redshift 3-4, right? And so that if you really want to know what is the fraction of progenitors that make the events, that's different numbers.
Okay, so you're saying the IMF might be different low velocity environments earlier?
No, even the overall star formation rate.
It's just a star formation, right? So
Yeah.
the star formation is a factor of 10 higher.
You also probably have some freedom in IMF, but the real freedom is in the overall star formation.
Sorry, so that's relative to the Z equal 0 core collapse.
Yeah.
Okay.
Which is a dangerous, on the one hand, it's a dangerous thing to do. On the other hand, no one has a feeling for what these numbers mean, and so I still think it's good to put it out there.
So it really, it's really important what the delay time is, right?
Yeah, the lay time will fold in. You cannot do science based on comparing these numbers. Okay, enough confusion for the. Let me skip a bit ahead. So you know we have 10 detections, we know masses. That's the one I like. That's from a different conference. I'll explain that some other day if you want. We know spins. That is not telling you what the common envelope efficiency is yet, but as a whole population, you need to come with a fitting story. And that's what I wanted to say. So this is the classical channel to get 2 stars or 2 cores of 2 stars close together. There are alternative channels. And so the last bit, I want to discuss a few insights, I don't know if I should say insights, that come from population synthesis today. Knowing that we have many assumptions in population synthesis today that I think within 1 or 10 years we know is very wrong. But let's do this in iterative process. If we take this at face value, what does it mean? Which progenitors should we be looking at, right? So that's the type of question. Oh, and this goes quicker. So how am I doing on time? I think I was a bit optimistic here.
You got still 10 more.
Okay. So this is the most classic, insightful picture from Brzezinski's review in the 70s. And so we have been discussing how wide are these binaries. And so the thing you need to compare with is how much do stars swell, right? The first question is when does the first star fill its Roche lobe? And so you can put some time axes here. This is for the 5 solar mass star that is actually his image. And so yeah, for a long time this star spends on the main sequence and expands by a factor 3-ish or so. And so stars are not so likely to fill their Roche lobe on the main sequence, except for massive stars where you really have an over preference for such close systems. But regularly, this case A is a bit more rare. For the O-type stars, I don't know if that's true. Case B, that is the part where the star crosses the Hertzsprung gap. It's shell burning. That is the biggest expansion. You can also see it here. The first part of this, the star has a radiative envelope, and the last bit it might have a convective envelope already, which Brzezinski didn't show yet. But it might be a very different outcome of if a star with the radiative envelope fills it Roche lobe or not, right? But this is where most room is. What is most interesting for making gravitational wave progenitors with heavy compact objects is to try and avoid mass loss here, because if you do that, you get a naked helium star that will have a wind. It's better to strip the envelope afterwards, if you were able to, because then helium ignition happens here, and this star happily burns helium into heavier things, and then has very little time to live afterwards. So if you strip it here, that's the best chance to get very massive progenitors. The problem is, this is a diagram for a 5 solar mass star. This is not what the diagram looks like for 20, 40, 80 solar masses, right? I have a billion of these models somewhere, but I didn't make the right picture. What happens for massive stars is that this window for case C is very, very small.
In terms of time,
in time also, because they're fast and there's a fast phase. But what I mean in terms of how much do they expand, and so what is the initial range of separations for which you would go through KC? Yeah. So I have different ways to and then I'll skip this. And then one bit in the kitchen of population synthesis is what we often do is to ask ourselves, okay, now we have asked the question, does the star fill the Roche lobe? Second question, is it stable or not? Fair question to ask, but there's many simplifications there. That's an instantaneous question at the moment it fills its Roche lobe, and what we usually do is compare. You can do this beautifully. You want to compare what is the Roche lobe going to do if I would peel off this first gram of mass, and what is the star going to do? And so if I peel off a little bit mass of the star and move it to the other star or throw it out, the Roche lobe will shrink or widen, and the star will shrink or widen depending on what it wants to do. And so if the Roche lobe shrinks, but if I peel off mass of the star and the star expands and the Roche lobe expands at less, then we get into a stable situation. And so this is this, I call this the zeta circus, all the zetas, it's this power law exponents to write this down, right? It's just saying, I peel off a little bit of mass, what is the Roche lobe doing? I peel off a little bit of mass, what is the star doing? And so you want to ask yourself the question, on what time scale, right? You can ask yourself, if I do that quickly, the star first will have an adiabatic response, but if I do it relatively calm, the star could have time to regain its thermal equilibrium. And so this looks like physics, but it's very little physics actually. It's only instantaneous considerations. So this is one of the things in population synthesis. It doesn't consider that, so these values usually come from single star models. But while you're transferring mass, you get a very different star and stellar structure, and we don't have good ways in population synthesis to do this. MESA doesn't need these things. MESA is just code like MESA is actually following what the radius are. So that's just to a bit of warning. So yesterday I called Javier, as one of my master students, to make a few plots that I hope are a little bit insightful. So the plots next are, they're not directly meant for publication, and the credit actually goes to the people that made this code, and that's the PI is Ilya Mandel here. This is the Compass code. It's population synthesis, very similar to many of the other population synthesis code out there. But he was the only one I could convince to make this on the spot. So I wanted to look for a moment at a slice through this multi-dimensional parameter space of all the outcomes. And so I asked him to fix the primary star to 20 solar masses. But we'll look at the parameter space. We'll have so many colors, so I'll try to explain the axis first while I still have your attention. So here I will put the separation of these systems, and here I will let them vary in initial mass ratio. Right, and initial separation, we already talked a bit about the radius evolution, so you can imagine that maybe the case A system will end up here, the case B here, the case C here, and then at some point you don't have interaction. And so it's actually Monte Carlo simulation, so if you wonder what is all this nonsense, it's because it's actually points from the Monte Carlo in this plane. And so there's a lot of structure here, and I will guide your eye a bit, and we can, for the people that really enjoy this, let's skip some of the details, but you need to see case A. The window for case A is here, the window for case B is here, for case C is here, and then this is not interacting by mass transfer. We can discuss if winds can do something. So what I wanted to draw your attention to for the moment is here we used a common envelope alpha of 1, because we don't know what better to do. And so if you have a look at orange and green together, the orange and green part is where this code says, based on the zetas, I'm going to be unstable. I've made slightly different assumptions, so let's not talk about that. But all of these are unstable and enter common envelope, but only these, there's so much energy in the envelope, and these stars have so expanded so much that only here the envelope is ejected. And all these orange ones in this particular simulation lead to a merger. And so one of the things I want to say with this diagram is this is a small bit of the parameter space here. We should not only be focused on systems that eject, but there are indeed a large fraction of systems that will, that are likely to merge. So there's a few more points.
I think those are actually the ones that mostly do observe. But we could talk about this.
So when you say merger, do you mean before it becomes degenerate, or what stage?
Yeah. In this case, the stars merge. So here it would be a star that is hydrogen shell burning merging with a lower mass companion. And that can be relatively long-lived. That the product still has to go through helium burning. That's 10% of its lifetime, right? So, these boundaries really change if you play with the physics here. And so one thing you could change with, let me show you what a different alpha does, right? And so I hope you get some intuition for it. I make the efficiency of ejection larger. Yes, it's easy to eject, so the things that were gonna merge are now becoming green. And well, I could go further. This is alpha is 10. And so suddenly I also get very interesting systems here. Now these are not shrinking so much anymore in this particular simulation. So that maybe they don't make gravitational wave events anymore, but they make other interesting products. So case A systems, population synthesis does this very poorly anyway, so let's not worry about those too much. Let's do that with detailed simulations.
But those are, just me understand though, the ones at the bottom there, in terms of making massive black holes, that can be super helpful, right? Because they're such a low Q that you would end up with
in this particular 20 solar mass star was the low end anyway, so this is a 20 solar mass star with a 2 solar mass companion. That's fun, but that can make interesting objects, but not gravitational wave sources. Not for LIGO at least.
So in this particular case, can you describe a little bit more, the alpha and lambda sort of prescription? So you don't have the internal structure of the star.
No, we have a fit to the internal structure of the star. There's some details of which group we take that and of there's, but the lambda comes from fits to single stars.
And when you do a common envelope alpha, do you take into account the binding energy plus or minus the accretion radius, or just above the orbit?
We can vary that. I have to check what we did in this particular one.
Because that changes the energy almost by a factor of 5 or 6.
Yeah. Any of these boundaries can change. I'm trying to show you some. I have some more conceptual points I want to make with this. So there's one thing I wanted. Yeah, sorry.
Just want to point out the mergers are of interest too, because you had a triple. And you had mass loss at the higher metallicity region where the mass loss kept the black hole. By itself, the black hole mass would be less than 30. Say, you could rejuvenate that star with a merger, and then maybe get something
really
later.
cool. I'll leave it to Hagai for the moment, or to Sylvia actually. Will educate us over the next years, aren't you? No. So I want to point out one more thing. The question whether mass transfer is stable is not the full question. The question is also, if it's stable, you would transfer mass to this other star, and what it will probably do is swell up. And so what you see here is MESA-like calculations. It's just Peter Eggleton's code, but I mean, it's really solving the equations. And this was some more poster I did in my PhD thesis, but never published. But so this is a star of 4 solar masses, and let it decrete at different rates. And if it decreases at a gentle rate, it will increase in mass, but it doesn't go up in radius much. If it decreases at a rate that is much faster than its own thermal rate, it will swell up a lot. Right? You get a star, but it's not a star in thermal equilibrium. Now, typically, in mass transfer cases in binaries, the second star has a long thermal timescale. And so typically, it gets mass at a much faster rate than its own thermal timescale. So this kind of swelling is very, very typical in binary systems. So, I mean, many of you, for good reasons, put their secondary in a common envelope as a point mass, right? I mean, you can imagine that you want to spend your computational time elsewhere. But the secondary might not be a point mass at all, right? So this is common envelope where one star fills its Roche-Lobe, and the second star is an actual star. It's out of thermal equilibrium, it's swollen, and its second star fills its Roche-Lobe, and its envelope is not super low density. We can get profiles from MESA if we want to, but that's an expanded star, right? And it's the envelope of the second star that causes contact and is initiation of common envelope. That's a different situation than we have been computing. Maybe the first approximation is not so bad.
It has been taken into account in double core evolutions in the past.
Yes, sure.
But it usually plays a role when you have a slow spiral in, so you actually have a time of a secondary to adjust. But during the dynamical common envelope event, it will be just the secondary has no time.
Dynamic, yes. So
its dynamical time is.
Right.
So this becomes interesting if you start with stable mass transfer and the secondary can swell up. And sorry, I'm probably not giving enough credit to people that have been looking at this. So these points I've been making much before.
I mean, this is like what happens in Nokia, right?
So let me see what it does. Right. So this is the picture I showed you before, and so all this blue stuff is stable mass transfer. But if I said the secondary is truly swelling, which is actually we don't know how much it swells, but if it does, then this picture would change to this. Yeah. Is that all entering a common envelope? And then, well, with this particular alpha, that's a huge amount of mergers, right? Yeah. There's almost no state. So let's say that alpha is higher, or there's other ways to do energy, then I could also make this green, obviously. Well, that's.
Sorry, what was the argument again that the secondary swells up?
In this part of the diagram, the donor star and the companion are relatively similar mass, evolve on similar time scales, and the secondary can probably deal with the mass. If you go here, the companion star is lower and lower mass, has a longer and longer thermal time scale, and will have a harder and harder time to deal with. If you go in this direction, the donor is more evolved, and it's also accelerating its. Now there are uncertainties here, and I think Kenta, you also found this out. I think in one of your that's you as well, right? So this does depend on if you accrete, what is the entropy of the accreted material, Is it actually accreted onto that star? And what is the spin of this material is actually also a question. And so we don't really know this swelling amount. I'm just saying that it makes a big difference whether this is green, orange, or blue, right? And we don't know yet. And you would think that that's such a big part of the population that at some point
So
there would
what-
be a prediction that we see the difference.
Why does the swelling help it to eject the envelope as opposed to merging?
No, I'm making, so
Okay, yeah.
this is common envelope, but if I put alpha as 10, it also
okay,
holds,
okay.
yeah, I'm doing magic here. I'm just saying these are 3 options, and well, maybe alpha 10 is a bit optimistic, you tell me, but I can make large part of this green, and those are uncertainties that we have today. And depending on time, so this was the initial parameter space. We can also play a different game with this, which is a more dangerous game. But say, let's say you believe for a moment whatever we did in this population synthesis, and we made a couple of binary black holes that were close enough to merge. And first thing first, there's a lot of physics assumptions I take along the way, and so I could get very different outcomes, and I should also explore those. But let's take one of these simulations at face value, and this is what is currently the default simulation, where default doesn't give it any extra preference than the others. And so I'm just showing things that make a binary double compact object that is close enough to merge in a Hubble time. And this is for a low, like 1/10 solar metallicity, if you want. And so down here, which you can't see, is the neutron stars. And then here in blue is the black hole neutron stars. And sorry, in blue, and then in black there's the black hole. And there's some funny structures that we are not going to look at because they will change if I change the physics. But what I want to do is, where did they came from? Right? So if these things went to common envelope, what should we have been simulating? Well, let's do one question first. This is the birth masses of these systems. And so you see, okay, neutron stars come from lower mass progenitors. That's not a prediction, that's what we put in the simulations. So keep that in mind. And then here's the black hole neutron stars, and these black holes, they come up to these crazy masses. And I hope you remember from our first slide that we don't really have observational constraints what stars are doing there, right? So this is all dangerous business, but let's say, okay, these are the progenitors. What should Paul be simulating when he, or anyone here, wants to do common envelope that led to this? In principle, these simulations can inform you what are the conditions right at the onset of common envelope. And so this is the parameter we could get out at least in the morning. And it's funny, so this is the mass of object 1 at the onset of common envelope, mass of object 2 at the onset of common envelope. So this was the original primary of the system. It's the original secondary of the system. So you see, all the secondaries are more massive, right? And so well, there's many lessons to take from this, but these stars are no normal single stars anymore by the moment they enter their common envelope, right? These stars were born with lower mass and have accreted on the way. They're already funny products on previous mass transfer. And they probably have gained mass before. And what this code is not very good at, but we know from other simulations, there's also simulations where you would have a long moment of mass loss before you go into the common envelope. Now populations is bad at predicting that, so I cannot show you. And then what kind of stellar types do they have? So the evolution is here as sort of discrete. We go from main sequence to Hertzsprung gap to, so sorry for the all the jargon here that we use, but in this diagram, it's a matrix of what is the stellar types that went into these mergers, and in black it's the black holes, and so this is the jargon that people use in population synthesis. So I tried to translate it here. So the Rushlope filling star, well, often it's a red giant with a convective envelope, which for bad reasons are indicated with these labels in this diagram if you want to know. It can also be a Hertzsprung gap star with a radiative envelope. Most often Hertzsprung gap star plus a compact object. So I don't think we have any simulations yet of those at the massive end, do
But
we?
those shouldn't enter common envelope, right?
The mass ratios can be extreme, so it can be in Hertzsprung. Well, it depends what you assume, but
All the objects universe are showing are Hertzsprung gap systems in one of the previous ones.
so should you do?
Yeah,
Yeah.
that's true, but I mean, with the radiative, but the
If you have a radiative envelope, what we think
convectiveness
is
of the
that the,
envelope increases as you go later, right? So, I thought
it depends
we
on
were
the mass
talking in
ratio.
those cases about the later case.
It depends on many things, but if the mass ratio is more extreme than 0.25, you have a heavy star with its envelope, and it has maybe it's a Newton star that tries to accrete. If you do that, it's such an extreme mass ratio.
This is the nuclear evolution that's driving.
Well, the shell burning, which is actually on a thermal time scale, but it's nuclear expansion, and shrinking of the orbit. The shrinking of the orbit is so much that it could be unstable. And
so even though with a radiative envelope it shrinks on mass transfer, it's what's driving its overall expansion is happening fast enough that it responds.
At the beginning of mass transfer, if the donor is more massive than what is accreting, that usually shrinks the system. And so the beginning, the mass transfer is driven by how quickly the system shrinks. If the mass ratio reverses, then it starts winding, and then it's the evolutionary expansion timescale. Both are roughly thermal-ish.
How big the more massive stars, the more stable transfers from radiative envelopes. Because for radiative it was very flat. We did the calculations, and you have so much stability that it's even embarrassing.
So I should point out, I'm not summarizing, but Natasha's group has some of the best simulations of doing this in an actual stellar evolution code where you solve for the stellar structure, where you can see quite a bit of this. And so the physics is not done very well in this population synthesis, so pay attention to what she's saying.
I guess maybe something else, I don't know if you consider this, but some of these systems don't just transfer mass by Roche-Loeb overflow, right? It's wind Roche-Loeb.
Yeah, we are considering these things that not in this particular model.
Okay.
But, yeah. So there's one group here that I think it's worth thinking about. It's stars that have already lost mass and are now mostly helium stars, maybe with a bit of hydrogen. That's also not companions we are considering at the moment. But for the double Newton star mergers, I think that's the type of interaction that is actually most certain that it has to go there, right? The moment the second Newton star forms, it has to be close already. So these companions can be this whole sequence, right? It could be main sequence star, helium star, Newton star, or black hole. It could be also a smaller helium main sequence star. So there's more variety there. So the last thing is, if I can still do the last part, this last slide. So one of these non-standard objects that can fill the Roche-Loeb is a star that has lost mass before. And so, you're probably not used to these diagrams, but these are evolutionary tracks of a standard binary that has a normal life detached, and it loses its mass the first time in gray, and it becomes a very hot star, but then it lives again. So then, even though you have taken off almost all the hydrogen, it can swell up another time. And some people in the community may know it, Thomas Tauras has given a lot of attention to this because these stars swell up, they can do a new mass transfer phase. You can see they swell up in this diagram because we put some dashed lines showing constant radii, right? So as a helium star, these things are less than the solar radii, but they can swell up during helium shell burning and be very big.
These are like born-again stars?
No, that's different things.
Okay.
But
Helium giants.
Helium giants. Now this is at high metallicity, where in this process you basically strip all the hydrogen off, and then there's not much left, and it does swell up. And it's mostly the low mass one. It is 2-3 solar mass. This is really the regime for Newton star formation, right? They're probably the small kick, so this is very important. Now at low metallicity, it turns out that this first mass transfer phase doesn't take all the hydrogen off. And so what we think is happening, and it's actually Ilva's work as well, that the opacities at low metallicity are lower, and just below the surface you don't have this iron bump, and so these stars already, they have lost most of the hydrogen, but there can be 1 or 2 solar mass of hydrogen left, but they already decide, I don't need to be big anymore, I'm going to shrink. And they make stars that live here. You can see they're bigger, like 1 solar radii to a few. That's where they live for the most of the time. We're interested in finding those as products before. But those, because they have the shell burning, they can expand a lot. And well, here we kind of magically remove the companion for a moment, but the companion could have been sitting here and have this extra mass transfer phase. And is those mass transfers stable? There's, I think, a lot of open questions there. But this is, I think, the phase you need to go through for double Newton star formation. And these are these 20 solar mass stars where we have at least some constraints. I would love to work on 100 solar mass stars, but they're all is in the air, I think.
How much mass is left? I mean, in that case, after the first mass, how much envelope mass?
I can quote the numbers for you. I can make something up at the moment, but it depends. Well, first is what do you count as the envelope? Because there is a layer that can be 2, 3 or solar masses that is a mixture of helium and hydrogen.
Well, the point I mean, when you expand that again, you expand it to what mass that envelope has.
I can quote it to you tomorrow. Yeah. In the order of a solar mass. So yeah, one of the questions is that probably easily ejected. The question is, can you actually shrink the system if that common envelope, which is probably where Natasha is going, right? Yeah. Sorry, I tried to fill in some. I don't have a conclusion slide. I think my main message is the first bit was more, well, not really observational, but we should be paying attention to the immediate aftermath of these common envelope systems. And I think even as theorists, we have to tell the observers what we want and what to look for, because they might not be obvious, and maybe you need to look harder to find them. But I think what we see with Ilva and Maria, that we really start to find some of these products. And so the second part, I try to say, if we play this game and try to think what is the channels that our current models predict, it's very dangerous to do, right? Because if we only look at those, if we have a poor code that says these are the channels that dominate, and we start to model those with a detailed code, do we ever learn which channels were really the ones that dominate? I hope that we make this loop enough times that it's, at some point it converges to an answer.
All right, so we have about maybe 5-10 minutes for discussion to go over time. But we had a lot of questions during some of the conference. So actually, any questions or comments?
Sorry, I don't want to monopolize, but so inflation, right, should change the radii of the star class. So can you comment on how that would change some of your expectations?
I mean, we were hinting it with Matteo, although we didn't quite explain. Maybe the you want to do the 2-sentence summary, or the 5-sentence summary of what we were talking about? Maybe everyone
yeah,
follows.
so I think the problem with inflation is going to be for single stars, it's obviously more severe as you go up in luminosity and intensity.
Maybe not everyone knows what inflation even.
Right, so the inflation is this idea that we don't really know exactly the other structure of this massive star, because in the 1D calculation we adopt mixing and theory to transport the energy, which would result in an hydrostatic liquid structure. And as the luminosity goes up and we get close, we get into limits, the MLT breaks down basically. And so the resulting hydrostatic equilibrium structure depend on the details of the way you transport energy. And so it turns out that if you run this in 3D hydrodynamics calculation with radiation transport, the solution you get are different of the already pretty diverse type of outcomes that people with different codes using different flavor of the MLT in this region have found. So there's a clear uncertainty in the radii for stars about like, let's say 25 to solar masses already in the main sequence. Now the problem is potentially getting more severe now if we have the situation where every time we want to model the common envelope evolution, obviously we know that I'm going to be object with very high luminosity to mass ratio. So we might, every time you might end up in this situation where 1D is never going to help you. We know that already.
So we even have to change a lot of concepts, right? The fact the star fills its rush slope, what does it mean? Because you have this, if you have this inflated halo around the star, is that really the star? So it's easy for that to fill the rush slope, but most of the mass is deeper inside. So there's this simple idea of, oh, now the star fills the rush slope, it will transfer. Well, that holds. But what happens if you peel off mass of this halo? There have been simulations already by Jelena Petrovic, actually, early on. Was one of the first to look at this inflation. But I mean, you guys have. So you can ask yourself the question: if they have such an inflated halo and that starts to transfer mass, that's very gentle. The timescale at which a star can replenish this halo is a slower timescale than when a full star would fill its rush slope and the rush slope is shrinking at the same time.
Unfortunately, the structure of the envelope is nothing like what you see in 1D. It's dominated by turbulence. There is mass flows which are already created by the fact that you're close to the Eddington limit. How that interplay with mass transfer, that's a very interesting question that we haven't addressed.
What's the effective logarithmic derivative of the radius?
In this situation, I mean,
Yeah, but Yelena has done that, right? So.
No, I'm talking about the 3D radiation.
Oh,
evolution.
yeah. Well, maybe the 1D models have some predictive power in saying how fast you could replenish that if you were taking it off from the outside. It would not tell you the structure. Am I optimistic here?
So this is a situation where the dynamical timescale and thermal timescale become comparable, and the rate of energy transport is regulated by the turbulence, because that regulates the porosity of the medium, which regulates how much energy is affected versus how much is transported by radiation. Stan is around, I think. Yeah, so Stan is an expert on this very interesting physical situation where material becomes porous and radiation can percolate through this Swiss cheese kind of structure.
I think the short answer would be that this, if you were to peel this material off, it would get replenished on pretty close to a dynamical timescale. So even though the density and the amount of material that's in this extended envelope is small, it can get replenished very quickly.
Right.
So all the physics of Roche overflow, in principle, might be very similar to what it is in a drum. But of course, as when you 2D or 3D, it gets very complicated.
The mass transfer outside of that, even from the wind itself, it sort of leads into the wind naturally, doesn't it? So, and if you have that interaction, in a low mass star case, I guess Joe Chent has shown that wind Roche-Loeb mass transfer can, over a period of time, be sufficient to bring the secondary into common envelope after a long time. Maybe in the massive star case, the winds don't have enough time to do that, but if there's that interaction farther out, is that significant?
Depends. So the winds depends on the speed of the winds
Yes,
compared to the
a lot of
orbit, right?
masses,
If the winds are very fast, then it widens the system. If they're very slow, you can get tails and rain increment, and then that becomes very interesting.
All we've done.
Yeah.
But so before everyone is too worried, I think the problem is maybe at, what shall we say, 40 solar masses and over that you really get into this regime, and at more metal poor stars, you need to go higher in luminosity to get there. So I think 20 solar mass stars, this is not our issue. For understanding really the top part of the HI diagram, this is one of the crucial issues, and mostly also harming to what extent can we even use the observations to test even single star models.
Yeah, this population synthesis model predict the rate of black hole binary merger. These are coming likely from this out.
But it sounds like the way to handle this, I mean, the uncertainty that this produces is in the radius, not the behavior. Like if you compare, as long as you knew the radius as a function of mass and evolutionary time, you could set that equal to a Roche-Loeb limit and say, okay, yeah, that's where common envelope will happen, because it'll behave like a normal convective envelope when it's there.
We have different ideas of what happens if you peel off mass of a star there, but I would love to, I have to
Maybe,
I thought it was.
I thought the major uncertainty is in the
I thought it
radius.
was gentle there, saying it's on a dynamical time scale, so if you have
We'll
to.
talk over a bit more about this over lunch.
All right, okay. Thanks, Tom, again.